Dara O Briain. Welcome to my school of hard sums. We're here to settle one big question, which is, when it comes to tackling practical, everyday problems, what is the best approach to adopt? Should you go with the cool, calculated techniques of maths and science, or just go hot-headed with all guns blazing and trust to luck?
This show is a battle of brain versus brawn, and tonight I shall be playing the role of brain. Each week, my grey matter is pitched against the brute force of my two comic guests, as we tackle three increasingly fiendish problems that we've never seen before. Oxford Professor Marcus de Sotoy is here to set the questions and decide whose approach is the best. And to keep us all on our toes, there's a bunch of brainy math students having a crack as well. But first, let's meet my competition for tonight. Tim Key and Alex Horne.
Gentlemen, welcome, welcome, welcome. Obviously, Alex, you are a graduate of the School of Hard Sums.
Yes.
Yes, you did.
Very proud.
Thank you very much. And you actually defeated mathematics practically the entire way through last time.
Yeah, it was, I think, the fourth greatest day of my life. So not as good as the birth of my children, but better than my wedding. I enjoyed it more. Like, as a day, I enjoyed the day more.
Yeah, good. Well, you know, there's high points and low points in weddings, but you don't, at the end of it, get told that you're the winner in quite the same way. You should.
But are you? Oh, hello.
I was at his wedding.
Yeah. How was it?
It was a damp squib.
It's
okay.
Very long service.
Yeah.
You, as a poet, Tim,
yeah,
they're not far from theorems or equations in their perfection, I feel.
No, they are quite sort of cynically, mathematically produced.
Oh, really?
I've stopped it. Yeah, I farm them out now.
You churn them out?
Yeah,
there's a machine.
yeah. There's a definite formula.
But are you a puzzle solver?
I like a cryptic crossword, but I'm more sort of, I'm letters rather than numbers, really.
I hate the numbers. You know, countdown, the numbers bit.
Not for you.
No, I just think it's bad telly, you know, maths, and it doesn't really work.
Right,
you know what I mean?
Welcome to our show.
On that sign-off, on that endorsement, maths just doesn't work on telly. We have a theme. We have themes this week, aren't we?
We do. It's about how maths can take you all the way.
See, we're back to your happy wedding day.
All the way.
All the way, exactly.
Yeah.
So this is a problem about frogs. There are 3 green frogs and 3 purple frogs and 7 lily pads, and they've got to get from one end to the other. So we've got 3 green frogs on the lily pads on this side, 3 purple ones, and you have to exchange them. They can jump to the lily pad that's free. They can jump over another frog, provided it's a frog of the opposite colour. They can only move forwards. So the challenge is how many moves do you need and how should it be done? What's the strategy?
OK.
So frogs can only move forwards and by one empty space at a time, unless they hop over a frog. They can only hop over frogs of a different colour to themselves, and can only hop one frog at a time. There are lots of rules in nature. How many moves for them to all swap places?
Make sure you...
Is he safe now?
Yeah. Lovely leap.
I think that was just about to go.
And you can only leap over... You can leap over 2, for example.
No, it can only... That's very good point.
What do you do?
Because you just coax them.
You just pop it out.
OK.
2 moves so far.
Should we keep that guy
Yeah, let's
pushing
keep
on?
that guy going. Oh, it's going to go.
Oh, sorry.
3 moves.
OK. Do you want to... I think it's 3 moves, isn't it?
Yeah.
4 moves.
You're keen on getting him there.
Yeah.
OK. Well, he's getting
Dara.
involved. Thanks, Dara.
5 moves.
Thanks, mate.
Part of the whole time.
Yeah.
Sorry. Grant. Right, where now? Yeah, there we go.
OK, good.
6 moves. 7 moves. Excellent.
Right,
Great.
We won?
No, we can't
so
do
you've got
anything
1
now.
across. And now...
We can't do anything.
Oh, God!
Don't worry. Don't worry, seriously. Shall we start again? Can we start?
I think you better reset,
Okay.
because that strategy didn't work.
Should we try doing the same?
Do the same again?
Yeah.
OK, we're just going to do the same again. Just recap.
Well, we like
So
patterns.
it was that first one that worked. 1,
Yeah, good.
2,
Yeah.
1...
3 comes next. Sorry. What does it? Oh, I see.
He's got to come.
I think if you have 2 colours together, you're stuffed.
But why?
Like there. I think
did we not get
that's
stuffed
a real
last time?
problem, because you're not going to be able to do anything. If the spare lily pad is back there, you've got 2 together.
We're not doing it wrong on purpose, mate.
OK.
OK. OK, good. Good.
Yeah.
Now, he's interested. So he can go there. He's got to go there. Now, wait a second.
Yeah, that.
He can go. No.
Then let's do it together.
You're nearly
Yeah,
there.
but he can go.
You're nearly there.
OK, he can go there, yeah?
Go back 1 move.
No, go back 1 move. Go back 1
one
move. Go back 1 move.
From
Okay.
there, you're nearly there.
OK, wait. Yes! Then go. Go.
No. Yeah, go on. Yeah. Bang.
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 Yes.
Go on.
Whoops.
Bang. Bang.
Yeah.
Wait. We can do it from here.
Start again.
You're actually 2 more moves away. One more.
Yeah,
you've got to get them mid-game,
so
yeah.
He's not going to jump by himself, do they? That's it.
There we go.
Oh, very
well
good.
Done. Well done. Congratulations. Very good.
I still think
That's
it's
the
impossible.
smallest clap I've heard.
Yeah, it gets smaller as it goes along. Are we illustrating anything other than the fact that you've got to keep them away from each other?
You can calculate how many you need to do. You've got to move the green ones 4 steps this way and the purple ones 4 steps that way. So you've got 3 times 4 for the green moves, that's 12.
Yeah.
Another 12 for the purple, that's 24 moves. But you've got jumps involved.
And each jump is a second
So the
move,
jump does 2 lily pads in one go. And you know how many jumps there are because each frog's got to do 3 jumps over the other one. So that's 9, so you take 24 minus... It gives you 15, which is the number of moves you made.
There's no way of doing it with a lesser number of moves.
Exactly.
Or greater
the number of
moves.
moves is forced on you. There's sort of two moves you can make, and one is a false move. So essentially, there's if you can do it, you'll do it in the minimum number. So what if I added another couple of frogs at the end, though? Could you tell me how many moves there are? I won't get you to do the moves, but could you tell me how many moves there will be?
So you're doing the same again?
Yeah.
Do you want me to just tell you? Yeah, there's 24 moves.
24 moves.
24 moves.
And if I add another frog?
If you add another frog,
34.
No, if you add another frog, 35 minutes.
35. And if I add another frog?
Just off the top of my head, that would be 48 moves.
48 moves is correct?
Yes. You're wondering
how is he doing this?
How am I doing this?
Got an ear.
First number of... Well, OK, so 3 frogs is 15 moves. 4 frogs is 24, isn't it?
Yes.
Yeah, now it goes on. This is basically
3 times 5.
4 squared minus 1.
Oh.
OK, and
5
that
squared
is
minus 1.
5 squared minus 1. All right, and we're presuming that as we go down, like 8 frogs would be...
80. 9 squared minus 1.
Yes, good for you. Very good, yeah. 9 squared minus 1.
The important thing to notice is that each frog needs to move forward 4 lily pads. And in a world without hopping, that would mean 6 frogs moving 4 steps each, so 24 steps in total to get to the end. If only life were that simple. Hopping changes everything. Because to get to the end, all 3 green frogs must hop over all 3 purple frogs. Or they can be hopped over, it doesn't matter. Because the total number of hops for all the frogs to get past each other stays the same. And that number is 9. 3 frogs times the 3 frogs they have to pass. And as each hop saves us 1 step, we can subtract that 9 from the 24 required steps, meaning all frogs can reach their destination in 15 moves.
Well, I think of the winner there. I don't know, you did find a way, but I do love your algebra, Dara.
Thank you.
Yeah, I think, the first round does go to maths for some beautiful N number of frogs. So, yeah, Dara and Brain wins the first round.
Well done, Brains, as well. Congratulations. Very good. Now, we have a second question, presumably.
We have, yes. This is a question, a maths of getting you all the way. This is all the way in a game of rock, paper, scissors. But it's a rock, paper, scissors race. So I'm going to get the 2 of you racing against each other. So the idea is to get the best strategy for this game. So actually you start on this square in the middle of the racetrack. The idea is to win. One of you has got to cross the line here. If you win with rock, you go forward 1 space, and your opponent goes back 1 space. But if you win with scissor or paper, you get to go forward 2 steps, and your opponent goes back 2 steps.
Wow.
So we're trying to work out the best tactics to employ in a rock, paper, scissors race, where victory with rock sends you forward 1 space and sends your opponent back 1 space. But victory with scissors or paper sends you forward 2 and your opponent back 2. 5 moves forward will take you over the line to victory. But how are you going to make them?
So we're going to play this game, and as we go along, you might be able to formulate a bit of strategy.
OK.
Dara, you've got to be using your sort of game theory strategies that...
Jesus, yes, this is...
So if you like to put your fists out, ready to play. Ready. 3, 2, 1, draw.
Oh,
OK, so there we go. So paper wins 2.
Yeah,
so you go forward 2 steps, and you go back 2. OK,
I
excellent.
have to do rock again, though, because I just think it's so much stronger than the others.
Okay. In fact, apparently research has been done that most people do rock to start
I'll do
with.
rock.
So you're already ahead in your game theory. 3, 2, 1, draw.
Oh, now again. Sorry, can I just... What is that? That's like a Star Trek thing.
Oh, I broke my finger playing football.
Cheeky monkey, that was... That could have been either.
Yeah, exactly.
Okay.
Well, the variation on paper is to do it palm up. And that's called feeding the horse. It's meant to be a great insult to your opponent.
I'll do that one.
Yeah,
You've
OK.
got quite a lot of additional information about everything.
Well, I've taken part in an international rock, paper, scissors championship in Philadelphia, actually.
No,
Got through to the semi-finals.
I know where you got the information from.
All right, next round, OK? Are you ready?
Yeah.
3, 2, 1, draw.
Yeah.
3, 2, 1, draw. No, player scissors, move forwards 2.
Okay.
So back 2 for you.
You
I think
celebrated
you
a
should
bit
be
early.
equal.
I'm
so
here,
yeah,
okay,
exactly.
You start
All right.
celebrating very early.
Okay, fine.
Right, we're going to test out a few more games of rock, paper, scissors. We're going to have a break. Join us afterwards when we finally tackle the show's big problem this week, and you and I will learn why exactly Alex and Tim have been getting up to this.
I think we should ditch the dice.
Got a spade. I mean, it shouldn't take this much.
No, it shouldn't take it, and if I was doing it, it wouldn't take this long.
Welcome back to School of Hard Sums. My comic guests Alex Horne and Tim Key are halfway through a game of rock, paper, scissors. It's also a race where victory with rock sends you forward 1 space and the competition back 1 space. But victory with scissors or paper sends you forward 2 and the competition back 2. As we rejoin the race, the comics have found themselves neck and neck, right back at the start, 5 spaces from victory.
Do the students have any strategies for this, do you think?
Yeah.
What do you think they should be doing?
Should play scissors.
Always throw scissors.
Always throw scissors.
Okay.
Yeah.
Well, actually, no, not all of you try that, because then you'll both just play scissors.
We'll be here forever.
No, but I think I've got quite a good countermeasure.
Good. Excellent. Right. OK, 3, 2, 1, draw. What are you doing?
Yeah.
2 scissors, yeah, OK. 3, 2, 1, draw. Scissors again. 3, 2, 1, draw.
Yeah, I mean, I'm not...
Yes! OK.
But it's only one,
so
though,
more
it's only
forward,
one.
move forward 1.
It's only one, though, isn't it?
So playing scissors all the time, you've got to throw some rocks in there. OK, 3, 2, 1, draw. Right. Ooh,
She said 2 scissors.
Yeah, OK. Turn and face. Fists at the ready. 3, 2, 1, draw.
But then it's only one, isn't it?
Oh, yes. Right, 3, 2, 1, draw. 1, 2, 3, 2,
you really
1,
want to win?
draw. Yeah, he really wants to win.
does,
3,
doesn't he?
2, 1. OK, that's 2 that way. Right. 3, 2, 1, draw.
Bad luck, mate.
Oh! Alex, you won. That's excellent. OK, let's see. Dara, have you got some strategies out of your maths?
Well, OK, well, see, there's very clear... What's known as the expectation values, which is if you carried playing over a long period of time, which would be a positive, which would be a negative. How we turn this into a fraction of time that you should choose, or when you should choose, I do not know. But clearly it is scissors that you should go for, right? Because the expectation for scissors is a summation of its expectation when it plays paper, when it plays rock, when it plays itself, right? So it wins big, it loses small, there's nothing there, so it's positive. And you do them for all 3, right? So generally scissors, positive, right? How that turns into a fraction, I don't know.
You can mix it up with paper if they're learning to play better. Mix it with paper because the expected value of paper is 0, so it won't change anything that you do.
So yeah, the order in which you want to do them is presumably scissors, then paper, then rock. Rock is your least likely one to do.
OK,
Is there some sort of ratio that should come out of this?
Yeah, mathematics, you can actually come up with an exact percentage that will optimise your moves in this game.
Are we 2 steps away from coming up with that exact
Quite
percentage?
close, actually.
Oh,
yes,
really?
Yes. And your little payoff matrix, which you had down there, which is kind of comparing what they're doing and what you're doing, is one of the keys to working out the values in this problem. If you play normal rock, paper, scissors, it's just random, so you just, on average, you'll do a third of each. As soon as you start doing anything different, they'll sniff that out. Because people tend to do rock more than anything else because it's easier to keep it there.
Yeah.
In fact, when I played in the Rock, Paper, Scissors Championship in Philadelphia to randomise things, I actually used the decimal expansion of pi. And so if the digit was 1, 2, 3, I'd throw rock, 4, 5, 6, I'd throw scissors, 7, 8, 9, then I would do paper. And I managed to get through to the semi-final of the Rock, Paper, Scissors Championship in Philadelphia using
Yeah, but were you
strategy.
beaten in the semi-final by someone who you thought had a better
The person who beat me in the semi-final, I discovered later, had a tattoo of a Fibonacci spiral on his arm, so I realised he was a maths geek and had actually clocked what I was doing and knew the decimal expansion of pi better than I did.
And what were you dressed as?
That's funny, because people did dress up in weird costumes, but I just went as Marcus de Soto.
Of course. Well, it's your stag, isn't it?
But that is his signature look.
And that's already you can see why scissors is better, because on average you're moving 2 forward and 1 back. Paper is pretty out, it doesn't really matter either way. Rock is the worst because it's pulling you back. So you think it should be scissors first, paper next, rock third, but that isn't what happens when you look at the maths, actually.
Really?
So it turns out you need to do rock as many times as you do scissors. And the way you can work that out is to stick a few probabilities in. So the probability of your opponent throwing rock, we'll say, is X, scissors is Y, and then that means that the probability that they're throwing paper is 1 minus X minus Y, because probabilities have to add up to 1. So the probability that you throw rock will be P, scissors Q, and then the probability that you're throwing paper will then be 1 minus P minus Q.
Right.
And then you've got to see, according to these probabilities, what's the expected number of moves you'll make, according to these probabilities and the payoff matrix.
To win this game, you need to know which option is most likely to move you forwards. If you choose rock and your opponent chooses rock, nobody moves. But if you choose rock and they choose paper, you move back 2 squares. And if they choose scissors, you move forward 1 square. Add these together and on average, choosing rock will move you back 1 space. Repeat this method for the other options and you'll find that on average, choosing paper leaves you standing in the same place and choosing scissors moves you forward 1 square. So why not just play scissors every time? Well, if your opponent spots your sneaky strategy, all they need to do is play rock every time to win. So the trick is to add a few rocks and papers into the mix. And this is where game theory comes in. Using these crafty probability equations, you can calculate the optimal ratio between rock, scissors and paper to maximize your chances of winning. Unless, of course, your opponent is a game theory expert too, in which case, you just cancel each other out.
Okay, I get that, even if you don't.
Okay, so...
And I
I
accept
haven't said
that.
that I don't get it yet.
No, but your face...
I don't get it.
Writes a poem.
So it's like in noughts and crosses, if they don't know how to play, you win every time. And then
Yes,
after a
because they
while,
do.
both people know.
Yeah.
You once had a game of noughts and crosses on my head.
Did I?
Yes.
Wow, how late in the night was that?
Very late, we didn't know each other.
Yeah. In a bar in Edinburgh?
Yeah, it was a bar in Edinburgh.
There we go. That's,
Is that what you used to do?
that is a lot of that, you know. Crazy japes we get up to in that festival town. Okay, that's very, very good. I find that very, very interesting.
So in the end, I think I won that.
You won
round.
that one. You definitely won that one. That's okay.
There was a little bit of you had
not enough. Not
there
enough.
was enough. You wrote down this little payoff matrix, which is the start.
I think this is like scissors meet scissors. We neither of us won.
We need. Okay.
Yeah,
okay.
yeah,
This is. We'll settle with a draw. Then.
Fine. Okay, fine. Fair enough. Okay, as you soak in this, and it is quite interesting, but it does take a bit of thought. Join us after the break when we will finally tackle the show's big problem.
But before that, here's something to ponder over the break. You're running in a marathon and doing pretty well. In fact, you just passed 2nd place. What position are you in now? Before the break, I asked, you're running in a marathon and doing pretty well. What position would you be in if you just run past 2nd place? Well, you'd be in 2nd place, because the person in 1st is still in front of you.
Welcome back to School of Hard Sums, the program that pits me using some brains against my fellow comics using brains and also brawn. In this case, Alex and Tim in a battle to find out which method is best for solving those normal everyday problems that life throws us, like competitive rock, paper, scissors. However, we've done 2 of these so far. They've been of a loose leaf of theme. What's the 3rd one going to be?
The 3rd one is a problem about office drinks. It's actually your leaving party.
Wow, this is no way to tell me, is it? This is
Exactly.
all the
Right,
way.
this is
This is the way mathematicians fire other mathematicians. What's happening at the party?
You got incredibly drunk. Suddenly you see your soon-to-be ex-boss coming towards you. You think, I need to get out of here, so I'm going to say something awful to him, and I really don't want to do that. But the plan of the office is laid out in such a way that you've got to make your way through various desks and things. Now, you're so drunk that every time you get to a junction, you randomly choose whether to go left, right, back or forward.
Okay.
You just haven't got a clue which direction is really out. But if you can't move, you just stay where you are and count that as a move. Okay. And what I want you to calculate...
You can't move.
Well, for example, if you get to the end here and you randomly choose to go to the left, well, you can't move to the left, so you just stay where you are. And what I want you to calculate is what is the average number of moves you need to make in order to get to the exit, which is
the top there.
The top there.
Wow, okay, fine.
It looks fairly easy to get out of.
You know me, when I get drunk out of things, I write in people's heads, I do all sorts of things. Okay, so you've already tried this. Let's have a look at how you started the problem.
You're leaving do at work.
Right, right.
OK, and you've had quite a few drinks.
OK.
Late into the evening, you see your boss guy coming over for a farewell chat.
I'm drunk.
Whoops. And you decide to make a dash
Yeah.
for an exit.
Yeah, I do.
There's 2 rows of 4 desks to get past.
Oh, God.
Total of 8 desks.
Usually fine, but I'm drunk. Right.
OK, so there are the desks.
Yep.
Oh, that's lucky. They put the desks in the right formation.
Right.
So there are 4 desks and they're 2 deep. If you weren't drunk, you'd just go, just be dup, dup, you're out. So we've got to work out what's the average amount of moves you can make to reach an exit.
Yeah.
Sorry, what's the average amount of moves you make to reach an exit?
Yes, moves, but yes.
So have one of these. I know, they're very silly. And then if you just drink this, this should do the trick. Get you drunk. Are you drunk?
No, that was water.
Yeah. OK, we need another way of generating randomness. This is the standard office cupboard. Oh, look, that's perfect. Have you seen, for example, dice? When you throw them, it lands on a number.
Let's see. I bet that lands on a 4 or something. 1.
That's
random. Cards. OK, so you wouldn't... If I say what card, you wouldn't be able to say what card it was.
Well, you say what card?
OK, what card?
That one?
Yes, it is.
OK. And these guys are just sort of... they're just like dogs. So we can see which one flips over first. So that's back and that's right. That sort of thing.
Jesus! OK.
So all we need now is a boss. We need a sort of small...
Old...
Well, mid-50s, mid to late
boss
50s.
guy.
Bald guy, ideally. You're perfect. Here he comes. You finished?
No, but I need to take a break anyway.
OK. I was just thinking, it seems like it's like a maths problem, almost, isn't it?
Yeah, it is.
So you could just do it with a sort of calculator or some beads.
Some abacuses.
Yeah.
I think it doesn't look insurmountable. There's just 8 desks. We're just doing random lefts and rights. I think we can solve it practically.
I think we can actually solve it.
So you think you can solve it, right? You've done this now already, so you're sitting pretty to a certain extent. I'm going to go over there and try to find some general mathematical way of doing this. Make up assumptions. I'll be over there. You can talk among yourselves, I suppose.
We'll just relax, Marcus.
Good luck.
Thanks. Yeah. Very kind.
You're at a party in an office laid out like so, and it's your leaving do. You're standing here soaking up the atmos when you notice the boss coming over. Not too keen for a chat, you make for one of these 5 exits. Only problem is you're drunk and moving entirely at random. How many moves will it take you to get out? Oh, and by the way, if you bang into a wall, it still counts as a move and an embarrassment.
So I guess that first challenge was producing a bit of randomness.
Well, we thought if we both go like that, then it's 2.
OK,
And if we went like that, that's also 2.
Right, so you do a lot of 2s, yeah. Well, there's a lovely example of randomness. The magic 8 ball. So do you want to ask it a question?
Yeah.
OK, go on. What's your question?
Who? Should we start with who?
So yeah, who?
Won the...
No, I don't think it could...
All right.
No, it's got to be kind of a yes-no, maybe.
Okay.
Did.
Yes, did.
Yeah.
Henry
Win.
his sort of first snooker game this year?
He's retired.
Well, this can tell you the future, and you're asking...
I'm completely new
Do you want to
Mabel.
ask it a question?
I've genuinely never seen one of these before.
Yeah.
So
Go on,
okay.
give it a go. It will read your future.
Where do you speak into it?
Ask it a question.
What? Can you hear me?
Yeah.
Will any
do
of
you think...
So do you think any of my children...
Just keep it light.
Okay. Will England win the FA Cup? What is it? Will England win the World Cup?
Oh. Should we see what it says?
But I thought usually it was more cryptic than that.
No.
That is really simple.
Well, I'm going to leave you with the magic 8 ball. You can keep on asking a question. I'm going to see how Dara's getting on with this working out. So, Dara, how's it going?
I think it's going OK.
You've got a bit of algebra going on.
I've got a bit of... Now I just have to cancel across, right?
Yeah.
That's the idea. But the idea, the basic 10, we'll get to this, is that really the sideways motion doesn't matter.
Yeah,
it just eats up moves. It doesn't actually make any difference to anything at all, right? So basically what's happening on this row is exactly the same and what's happening on this row is exactly the same at each of these points. Right? Yeah. So in other words, you're at any of these, A, B, C, D, or any of these points, you know, one move will take you out.
Yes.
Yeah. And 2 moves will just leave you on this row and 1 move will bounce you back to this row.
Yeah.
Okay, now here the situation is even clearer. 1 move brings you up, 3 moves just leave you sitting here, right?
Yes.
So what you do is you get the expectation of the row. And that's the only question I have is, am I doing this or am I
Yeah, what's it? The 5, I don't understand the 5.
I'm adding, sorry.
No, because wherever you are, you're just saying what's the expectation value now. What's the expected number of moves? No, you don't have to add those. So if you take the 5 off, you'll be...
Oh, right, okay, grand, we're close there. Okay,
you'll be very close.
Well, then I'll just discreetly tear up the piece of paper that involved me doing the equation for 5. OK, fine, OK, grand. OK, well, let me do that like whatever. Yeah, OK. I'm not questioning your methods, but I'm just saying. Look at this. This is all the work done with the 5. See that?
Beautiful.
See that?
Yeah.
All gone.
Just
all gone.
rip it all
Gone. Oh.
So actually, we can have a look at some of Dara's workings. You've got a little tablet there you can throw up. Oh, there we go. So what we've got here is ER1 and ER2, which is the expected number of moves you're going to make if you're in row 1 or row 2. So actually, what you're trying to work out is ER2, but you build it up in a recursive way. And so you can do a little formula, because there are sort of 4 possibilities. Suppose you're in row 1, there's a 25% chance you're actually going to get out. So this part of the equation is the move which gets you out. But if you move left or right, there's a 50% chance that that will happen. So you've got the half here, and if you've added a move to
He's trying to write on your...
I can see it coming up on mine. I'm intrigued.
I'm trying to do a snowman.
Yeah. And there's a quarter of a chance that you'll go backwards. So if you go back to the row 2, so you've added 1 move to there, and now you've got to know the expected number of moves from row 2. So this builds up the expected number of moves from row 1 to get out. And he's worked out a similar formula for row 2. And if he combines these, you'll do something called solving simultaneous linear equations, something everyone learns in school but doesn't realise why it's useful.
How's your snowman?
I've done a picture of Dara with an earring.
Oh, that's fantastic, yeah. This is good gypsy done.
Can you just tell me what he told you?
He said that he's talking about some of the stuff near the bottom, and then said that it's what you're left with is sort of quite a good simultaneous linear equation.
All right.
Yeah.
Which I can't solve.
If you really want to choose things randomly, then this is the book for you.
Is that pi?
A million random digits.
A million random digits.
I read that, actually, yeah.
So, it's a fascinating book. This is one of my favourite sections.
You can dip in anywhere, though.
Yeah, exactly.
It's like a toilet book, really.
It's amazing. So they used to use this to generate, instead of generating random numbers, they would just take this book and choose
It's the opposite of the book the magicians use. I had to do a mind-reading thing with a magician once, who I won't name. And he gave me a book and he said, what is the bottom word? Look at the word on that page, and I think of the page number. And all of the books are printed so that the last word on each page is exactly the same.
Really?
Yeah. And so...
You think it's not magic?
I'm just saying that this particular guy didn't, but some of the people you've seen that were really magic.
OK. Yeah. Can you say that 30% of magic is magic and the rest is tricks?
Just under, I think. You have to have like a certain skill set, and then there's you have to supplement it by at least 25 or 30%. That has to be
actual magical powers. Yeah.
Well, if you want to be like, if you want to earn money out of it.
Daniels.
Yeah, Daniels would be about 25, 30%.
Copperfield? How high is this Copperfield?
Oh, well, one sec.
This
is very good. This
It's
bit.
riveting. So, Dara, you got an answer. You're very confident over there.
Yeah, it kind of worked out neatly enough, and it wasn't like some crazy random thing. So it feels like there's a proper answer there.
Yeah, and you got an answer too, didn't you, I guess?
Yeah,
we got an answer out in the field.
OK, well, let's see how they did with their answer.
That's brilliant. Oops, what's your hat?
We're ready. So we need to do this several times and then divide it by those times to get an average.
OK, fine.
I'm going to generate the randomness.
OK.
So we're going to do the dice first.
So 1 to 3 would be left.
OK.
No, right.
10
to 12.
4 wild, yeah. Oh, I think the boss is coming.
OK.
Four of these. It's 3. So that's turn right.
OK. Now going right past this drunk...
Are you out of the building?
No. Roll again.
OK. 4. It's another left. That's 6. Left. 3. Right. 10. Forwards. Are you out?
Almost.
That's a 9. So that's backwards.
OK.
That's a 10.
Yes. Another forward, please.
And that is an 11.
I'm out.
So the first attempt, Tim, is 12.
I think I spotted the floor. We haven't rolled a 1 yet, have we? I think we should ditch the dice.
Cards?
Yes, please.
Spade, left.
The the same card.
OK, so that's left again.
Ace of hearts.
That's forward. Diamond, that's backward. Ah! The minimum is 2, the maximum is infinity. So it'll probably be, if you did the average of them, yeah. I mean, it shouldn't take this much.
No, it shouldn't take it, and if I was doing it, it wouldn't take this long.
I can't cheat it. It's just random. Well, I'm not going to cheat it. Oh, the boss is getting so cross with you.
This is what I'm worried about. Get me a heart.
Club.
Bye.
He's out of there.
How many?
26 moves. Dogs activated. Go right, go backwards. Go backwards and then left. Go right. Go left. Oh, go backwards. Oh, go forward. No! It's just this going out. Go on.
I'm going. I'm walking.
Yeah! 27. I thought maybe we'd get the boss out and spin him round on this chair.
Now.
Right. Are you ready?
Yep.
Back. Ah! Left, back, forwards, right.
Now.
Forwards! Yes! 2. That's the lowest so far. That's the lowest possible.
We're starting to be able to confront randomness and win.
Are you sure we got enough? I wouldn't mind carrying on just sort of like a hobby.
OK, so we have some sort of answer for this. What answer did you get, lads?
Yeah,
15.733333333 recurring.
That's impressive.
Yeah.
Not bluffing, mate.
OK, so, Dara, how many moves do you think, the expected number of moves to make?
I've gone for 8.
And students, what did you get? Expected moves. Well, I can reveal that the right answer is indeed 12 moves. This brain went... But I don't understand, Dara, because you have the right equations down.
I know why. During all that, in my rush and being happy with myself, this is the right idea. This is the right idea, which is basically it doesn't matter where you're on, on this row, doesn't matter. A quarter of the time you leave and a quarter of the time you go back down and half the time you just shunt backwards and forwards. So you can write down what's called the expectation of that as this equation. And you can do the same thing for here, because a quarter of the time you'll move up to here, and 3/4 of the time you'll do nothing of any importance. So you can write that down as that equation there. And they're surprisingly easy to solve, aren't they?
This is GCSE. We teach our students at GCSE maths,
easy, right? Yeah. This is correct, this is correct, this is correct. So we get that, and then you get this correct, this correct. You get that, they're the same. But for some reason, on the very last line, I added them up wrong. And I got 4 when I should have got 8, and I got 8 when I should have got 12. And this is why I don't run the Large Hadron Collider, because I have the right idea and I forget to add things. And the 2 bits wouldn't have met, and the 2 beans would have passed each other. And in fact, in an exam, I would have got... How many...
I would have given you nearly all the marks, because it's just... The working is perfect. It's just...
But in the real world, that's not good enough.
It's exactly like us. We're just 3.7333333 recurring up. And we did all that walking.
You did a lot more walking than I did. I did a lot sitting and feeling very smug for myself.
The key to working this one out is to spot that you only need to advance 2 rows forwards to reach the exit and escape the boss. But because you're drunk and stumbling about all over the place, you need to figure out the number of random moves you can realistically expect it to take you to advance from row 2 to row 1, the expected number of moves. Then add to that the expected number of moves to advance from row 1 to the exit, and you have your answer. Now here's the snag. One of the 4 possible moves you can make from row 1 will take you right back to row 2, where you effectively have to start all over again. This is known as recursion, and the best way to solve this tricky conundrum is with a simultaneous linear equation. And if you're sober enough to add everything up right, they reveal that the total expected number of moves it will take you to get to the exit is 12. Well done, students.
I love my method, but that's okay. This is the real world. This is not an exam.
Method.
You hated your method.
Yeah.
So I think I will actually give you the win, Dara.
I
am going to, because
I have
the workings. Look,
it's a lesson.
This is the kind of mistake
in the real world, Marcus. Workings don't count.
Yes.
By the way, can I just point out one thing? The students all stole my method. None of them are denying that. They just know how to do adding up at the end. Yeah, exactly. At the end of this, it is a dirty, unpleasant draw, with the students being the only ones, and even they came across like cheats. The only come out of this with any honour at all. But the method is great. That bit, oh, man, this is going to bug me that this bit was fine, the concession bit, and that bit just... OK, at the end of that really grim and unsatisfying episode of Dara O Briain's School of Hard Science, thanks to those rising stars, the students on our maths panel, thank you very, very much. You're doing great. Thanks to our inscrutable question setter, Oxford Finance Professor Marcus Sotoy, and thanks to our guest comedians, the new best friends of math, Alex and Tim. We'll have more of these tricky problems another time in School of Hard Sums. Thank you in an exhaustive way. Thank you very much.
And now time for your homework. If a group of office workers are standing in an evenly spaced circle and the 5th person is opposite the 17th, how many people are in the group? If you'd like to take a look at the answer or just cheat, go to the website joindave.co.uk.